Today we will continue the exercise 2.3 based on the Rolle's theorem and Lagrange's mean value theorem. So let us start from the first example. The Rolle's theorem is holds for the function x cubed plus px square plus qx plus 5 for x belongs to closed interval 1 3, and the c is also given that 2 plus 1 upon root 3. You have to find the values of p and q. So the Rolle's theorem is holds. That means the function is continuous on closed interval 1 to 3. Function is differentiable on open interval 1 to 3. And f of 1 is equal to f of 3. So we will use the third condition. F of 1 is equal to f of 3. So what will be the f of 1? We will put x is equal to 1 in this function. We will get f of 1. Similarly, we will put x is equal to 3 in this function. We get f of 3. After simplifying, you will get an equation in P and Q, linear equation in P and Q. This is our first equation. Now, there exists C in the open interval 1 to 3 such that f dash at C is 0. So we will find the derivative of this given function, and the derivative comes out 3x square plus 2px plus q. So we will find the value of this derivative at C. Okay, but C is given that Rolle's theorem holds for this C, 2 plus 1 upon root 3. So we will put C is equal to 2 plus 1 upon root 3 in this derivative and then simplify. So after simplifying, we will get 4 plus 2 upon root 3 times P plus Q plus 13 plus 12 upon root 3. Now by Rolle's theorem, f dash at C is 0. So this derivative must be equal to 0. So after equating the derivatives, we get the second equation in P and Q. This is the linear equation in P and Q. So from equation 1, again from this equation, we will multiply this equation by root 3. Okay. Then this is our equation number capital A. And this is from second equation. This is our equation capital B. Then what we will do, we will subtract the first equation from this second equation. We will get 2p is equal to minus 12. So p is equal to minus 6. Now put p is equal to minus 6 in any one of this equation, either this in first or in second or in third or in A or in B, whichever we want. But this is the simplest one, so we'll put p is equal to 6 in the first equation and then simplify. We get q is equal to 11. So these are the two possible values of P and Q. Now, the next example, Rolle's theorem holds for the function f of x is equal to x minus 2 log x, and the interval is given 1 to close interval 1 to 2. Then we have to show that the equation x log x is equal to 2 minus 6 is satisfied by at least one value of x in open interval 1 to 2. Again, the Rolle's theorem holds. That means all the three conditions of Rolle's theorem are satisfied. So f of 1 must be equal to f of 2. That is the third condition. And there exists a c in the open interval such that f dash at c is 0. So let us find the derivative of this function f dash of x. Here we have to use the product rule. First function as it is, derivative of the second function, plus second function as it is, derivative of this first. But I have not written anything here. So derivative of x minus 2 is 1 minus 0, that is 1. So no need to write. So x minus 2 into 1 upon x is 1 minus 2 upon x plus log x. So this is the derivative. Now f dash at c is 1 minus 2 upon c plus log of c. But by Rolle's theorem, the f dash at c is 0. Okay. So 1 minus 2 upon c plus log c is 0. Now take the LCM. Now c belongs to this open interval 1 to 2. So c is non-zero. So we can multiply throughout by c. So c log c is equal to 2 minus c, where c belongs to open interval 1 to 3. That means there exists c in the open interval 1 to 2, and which satisfies the equation x log x is equal to 2 minus x. Okay, so this is the solution of our problem. Now the function f of x is equal to x times x plus 3 into e raised to minus x by 2 satisfies all the conditions of the Rolle's theorem on minus 3 to 0. Find the value of c such that f dash at c is 0. That means actually we have to verify the Rolle's theorem for existence of c. then f of x satisfies all the three conditions of the Rolle's theorem as it is given, given in the problem itself. So there exists C in the open interval -3 to 0 such that f dash at C is 0. So initially we have to find the derivative of this function f of x. So here we have to use the product rule. As there are three product of three functions, so we minimize it by multiplying, taking the product of first two functions. Okay, so now there are product of two functions. So to find the derivative, first function is as it is into d by dx of the second function. Now e raised to f of x, its derivative is e raised to f of x into f dash of x plus this e raised to x minus x by 2 as it is into derivative of this x square plus 3x. So this is the derivative of the given function e raised to minus x by 2 into minus x square by 2 plus x by 2 plus 3. Okay, so it is given that Rolle's theorem is verified, satisfied. So f dash of c must be equal to 0 for some c. So this f derivative at c must be equal to 0, implies this equal to 0. But exponential function is never 0. Its value is non-zero at any value of x. So we will divide this throughout by this e raised to minus c by 2. Then we get minus c square plus c plus 6 is equal to 0. So taking this factorization, after factorization you will get x c minus 3, c plus 2 is equal to 0. Therefore c is equal to 3 or c is equal to minus 2. And but out of these two values, this which value, this 3 doesn't belongs to this interval, given interval -3 to 0. Only 2 minus 2 belongs to this interval. So this is the value which we want. Now we verify Lagrange's mean value theorem for the following function. Now we have to verify Lagrange's mean value theorem. Now what is the function? Log x. Now what are the conditions for Lagrange's mean value theorem? There is only one condition is different. One means one condition is less from that of the Rolle's theorem. The function is continuous on the closed interval. The function is differentiable on the open interval. Only these two conditions we have to check for the LMVT. As log x is a continuous function, there is no problem for log x. And you must know what is the graph of this log x. So I will show you the graph of the log x. This is x-axis, this is y-axis, and the graph of the function is like this. Okay, this is log of 1 is 0, so y is equal to 0. Okay, this is the function of log of x. Okay, so there is no break anywhere for this function, so the function is continuous everywhere and differentiable also everywhere. So both the conditions of Lagrange's mean value theorem are satisfied. Hence there must exist C in the open interval 1 to e such that f dash at C is f of e minus f of 1 upon e minus 1. Okay, this is the Lagrange's mean value theorem formula. So what is f of e then? F of e is log e. What is f of 1? F of 1 is log 1. Okay, so log of 1 is 0 and log of e is 1. So using that values we get f dash of c is 1 upon c. So from this equation put those values in this formula. F dash at c is 1 upon c, f of e is 1, f of 1 is 0, and 1 upon e minus 1. That is 1 upon c is equal to 1 upon e minus 1. Taking the reciprocal on both the sides, we get c is equal to e minus 1. And you can conclude that e minus 1 belongs to the open interval 1 to e. Definitely e minus 1 belongs to the given interval. So this is the required c. So by this way the Lagrange's mean value theorem is verified. Again, we have to verify the Lagrange's mean value theorem for this function f of x is equal to x minus 1, x minus 2, x minus 3 on the closed interval 0 to 4. As it is a polynomial function, it has to be continuous, it has to be differentiable everywhere. So in particular on closed interval 0 to 4 and open interval 0 to 4. Okay. So both the conditions are satisfied. There must exist C in open interval 0 to 4 such that f dash at C is equal to f of 4 minus f of 0 upon 4 minus 0. Now f of x is x cube minus 6x square plus 11x minus 6. So we will find the value of this function at the endpoints, that is at x is equal to 0 and x is equal to 4. Then the derivative of the given function is 3x square minus 12x plus 11. Now, as Lagrange's mean value theorem is satisfied, there must exist C, as I told earlier. So f dash at C must be equal to 0. So 3c square minus 12c plus 11 is equal to 6 minus of minus 6 upon 4. That means this 3c square minus 12c plus 8 is equal to 0. So using the formula to find the root of the quadratic equation, we get the root as 12 plus minus root 48 upon 6, that is 2 plus minus 2 upon root 3 belongs to 0 to 4. Okay, so the Lagrange's mean value theorem is verified and the value of CR 2 plus minus 2 upon root 3. Again, very simple example. This is the polynomial function. Polynomial function is continuous everywhere. Polynomial function is differentiable everywhere. Okay, so these two are satisfied by two conditions of the Lagrange's mean value theorem. So there must exist C, okay, in the open interval minus 11 by 7 to 13 by 7, so that f dash at C is equal to f of 13 by 7 plus now f of 13 by 7 minus f of minus 11 by 7 upon 13 by 7 minus of minus 11 by 7. What is the formula? F dash at C is equal to f of B minus f of A upon B minus A. Now take the function, take its derivative, take it, the values of this function at the endpoints f of that is at 13 by 7 and minus 11 by 7. At these 2 points we have to find the values of the function, then function and its derivative. Put x is equal to c in the derivative, that we get 2c minus 3. Then we will put all those values in equation number 1. Then if we simplified, then we reach to the value c is equal to 3 upon 27, that is 1 upon 7, and obviously it belongs to the given interval. So the Lagrange's mean value theorem is verified for this function also. Now again we have to verify the Lagrange's mean value theorem. The given function is 2x minus x square, okay, is a polynomial function. So it is continuous on closed interval 0 to 1. It is differentiable upon open interval 0 to 1. Thus f satisfies the conditions of LMUT theorem. So there exists C in the open interval 0 to 1 such that f dash at C is equal to f of 1 minus f of 0 upon 1 minus 0. Now f of x is 2x minus x square. Now f of 1 is 1 and f of 0 is 0. So f dash at C is f dash of x is 2 minus 2x and f dash at C is 2 minus 2c. So we'll put these values in this equation number 1. We get 2 minus 2c is equal to 1 minus 0 upon 1 minus 0, that is equal to 1. So 2 minus 2c is 1. So 2c is equal to 1. So c is equal to 1 upon 2. It belongs to the open interval 0 to 1. Hence, again, Lagrange's mean value theorem is verified. Now go for this next example. Here the function is a rational function. Okay, it is a ratio of two polynomials. Okay, and the ratio of the two polynomials means a rational function. It is continuous everywhere, probably except zeros of the denominator, where the denominator becomes 0. Now if you see here, the denominator becomes 0 at x is equal to 3 only. And if you see the interval, that interval doesn't contain 3. So this function do not have any problem at x is equal to 3. So as the ratio of the polynomial function is continuous everywhere and differentiable everywhere except 3. But 3 doesn't belongs to this interval, so the given function do not have any problem. So it satisfies the Lagrange's mean value theorem conditions. There exists C such that f dash at C is equal to f of 5 minus f of 4 upon 5 minus 4. Now f of x is equal to x minus 1 upon x minus 3. So now I am adjusting the denominator in the numerator, so that I have to use the only one single simple formula to find the derivative. Okay. Now f of 4 is 3 and f of 5 is 2. Now to find the derivative of 1 is 0 and derivative of 1 upon x is minus 1 upon x square. So, okay. So this is for this I have simplified this. Instead, if I have not simplified this, then I have to use the quotient rule to find the derivative of this function. Okay. So using this equation number 1, put those values and simplify. You get a quadratic equation in C, and whose roots are 3 plus minus root 2. Now if you see, 3 minus root 2 doesn't belongs to the open interval 4 to 5, but 3 plus root 2 belongs to the open interval 0 to 4 to 5. So this is the our required value. C is equal to 3 plus root 2, and we don't require this 3 minus root 2. So by this C, the Lagrange's mean value theorem is satisfied, verified. So we will stop here. In next lecture, we will start the increasing and decreasing function.